video is going to be kind of an exploration at first, but ultimately of how to find nth roots of complex numbers written in trig form. So in other words, like nth roots of any number, since every number is a complex number that we deal with here. But we're going to start by exploring something, some basic fundamentals here. But I say previously in our studies we've considered what it is to take roots of real numbers. In this section we're going to consider what it is to take roots of complex numbers, since complex numbers kind of encompass all numbers. Okay, so I say this here, x squared equals 25. This actually has two solutions, positive 5 and negative 5, but here's the deal. We'd have to take the square root of both sides to solve for this, and so we say that it has two roots. Okay, it has 2 square roots of 25. It says likewise, if we solve x cubed equals 8, our solutions will be a cube root of 8. Furthermore, if we took the fourth root of both sides of this, we would have like fourth roots of 81. The interesting thing is this, without showing my work, I can show you this. Here are the solutions to all of my equations here, and you'll notice that when I had to take a square root, at least a square root, a second root, I got 2 answers here. But when I take a cube root, I've actually gotten 3 answers. I got 2, and then I got negative 1 plus I root 3 and negative 1 minus I root 3, which are complex numbers. And then likewise down here, I say this was a fourth root that I'd have to take to solve it. So I get 4 solutions, positive and negative 3, but also positive and negative 3i. So here's the deal. What we're going to do is we're going to engage ourselves in finding all of these up front. So finding, oh my goodness, let's try to get that out of there. Finding all roots. And I'm going to say n roots, okay, because we're taking the nth root. So here's the deal. It says, notice that there were 2 roots of square roots at least of 25, 3 cube roots of 8, and 4 fourth roots of 81. Here's what I can tell you. At least in algebra, we can make this statement and be 100% true, but we say every real or complex number has exactly n distinct nth roots, okay? So if I were to solve something to the nth power, and I say it was equal to some constant, of course the appropriate move here would be to do this. We'll take the nth root of both sides, and this would solve it. All I'm trying to commit to knowledge here is this. In this video, what I'm saying is there have to be this many roots. And we want to go find them all, and we want to do it without having to do a lot of algebra, okay? So here's the argument I'm going to build. I said the key to finding these nth roots lies in the trig form of a number. The idea here is this. What we'd rather do is write our complex number, which is typically written in standard form, which is this x plus yi form. We want to write it in trig form, which is this r times the cis, or cosine I sine of some argument theta form. But if we can write it this way, what I can tell you is we can actually use DeMoivre's theorem, a form of it, to kind of manipulate these. But we'll say, here's my argument. We say, suppose that z and w are complex numbers, and what I can tell you is this: w is the nth root of z. That is, if I were to take z and I were to take the nth root of z, I would get w, okay? And so that's exactly what this is saying here, as a matter of fact. So kind of like, w would be 3 if this was the square root of 9, it would be like that. What I'm saying is if we raise both sides of this last equation to the nth power, the interesting thing that happens here is this. Of course, we know that algebraically speaking, when you raise an nth root to the nth power, what you build is this new equation where you get w to the nth power would be equal to just z. So in other words, this number z would have been this thing that we took the nth root of, to the nth power gives us z. That's exactly what these two statements mean, the same thing, written different ways. So what I want to do is I want to point this out. We say if we raise both sides of this last equation, we get this statement here. What I want to do is this. Suppose that z is some now number in trig form. Now this is r cis theta form. I've just written it all out, we say. And w is actually equal to some other number in trig form. So we say instead of like some modulus r and some argument theta, we'll say it has a modulus of s. We'll just call it s. And then we say it has an argument or a direction of alpha. That's its angle, okay? I say if we were to substitute these back in, so now I'm going to take this and I'm going to plug it in here and take it to the nth power. So I would get this. I would get essentially s, I'm going to write it this way, cis alpha. I would plug that in for w here in this statement, and that's being taken to the nth power, and that would be equal to z, and we said z over here is this r cis theta. So I have r cis theta. And using what we know about equality of trig form numbers here, and also this, using DeMoivre's theorem, we can at least say this left side now becomes this s to the nth power, or modulus to the nth power, and then cis n, or the power, times the argument that was already in there. So the left side becomes this, the right side becomes this, and essentially what we dig out of this is this. Well, then s to the n has to be equal to r because they kind of occupy the same spaces here. And then we say if these two numbers are equal, of course, then we would say that n times the angle alpha is equal to theta. So here's what I want to do. I basically wanted to, in all of this, solve for, say, this angle alpha, because this angle alpha is involved in the root, okay, the root. So we said this left side was w to the nth power equals, and we had z, our number here. So in other words, w is the root here that we want to find. What I want to know is then what are the root values, or at least what is the angle, and what is this value s? Okay, what is this root? So if we're going to find this here, basically we built this in. We say absolute values wise, we say that the absolute value of a number is equal to s to the n here, or root to some power is equal to what you get when you get the actual number. And then also this, we had n alpha down here. We said n alpha, that is, had to be equal to theta. Now you'll notice that when I say n alpha equals theta, in this instance I write plus 360 degrees times k. And if I wanted to make any note on this here, what we would say is this. This just includes all coterminal angles. So includes all coterminal angles. Remember, coterminal angles are angles that just land in the same space anyways, and so are equal to the original angle. So I'm going to make a note of this here. We do need to build that in, and I say k is just some whole number. It can be positive or negative or zero. But if this is the case, what I want to kind of point out is this. If s to the n is equal to r, then this question is, well, then what is s? Because here's the grand scheme of things. I'll have you look back down here. Remember w. W is the root. W is the root of the number. This is what we want to find, is the root of the number, okay? And we say that it's equal to s CIS, and I suppose I could write this in, alpha. So we need to know s and we need to know alpha. So from this right here, we could take, let's do this, we could take the nth root of both sides. And what I get is this, really. I get just s is equal to r to the 1 over n. Now, a quick algebra review, we say that this is the same thing as r to the first power, the nth root of that. So when you write 1 over n, you're really saying the nth root of this base, okay? But we say, well then, my new number here, if I were to take the nth root of some complex number, then the new number, I would just have to take the nth root of the modulus. So this is the nth root of the absolute value, or the modulus. That's all this is. So in other words, if I want to take a nth root of a trig form number, all I have to do is take the nth root of the modulus. Now the next thing we have to do is say this, well, if I solve for alpha up here, I'd have to divide everything by n in this statement. And the interesting thing is, then you arrive at this right here, we say then alpha, the angle, would be equal to theta plus 360 degrees k. But we divided everything by n. So what we get is this really here. We get the original angle, theta. And what we're going to do is we're going to divide by n. Now when we say what is n, we say n is the root that we're taking. So if I said fourth root, it would look like this, fourth root. It would also look like this, some base to the 1 over 4 power. And what I could tell you is this, n would be equal to 4 in this case. All right. If it was 10th root, then I would say it's something to the 1/10th power. And I could also say this, n equals, whoops, I was looking at the 4. N is 10. Scrub this out of here. But n would be 10, okay? And that is, apparent in both of those instances here. So basically, the angle we get on our root, then, would be the original angle just divided by whatever root you're taking here. And we also have to divide the 360 degrees times k by that root. So we're going to put this to practice, basically, and I'm going to show you essentially how this can be accomplished here with a number. But basically, we're going to summarize it. We say, to find the nth root of a complex number, what we're going to do is first find the nth root of the absolute value. And then the angle for the first root will be the original angle divided by the nth root. So if you're taking the fourth root, you divide it by 4. Or the 10th root, you divide it by 10. So basically, just take the original angle and divide it by this. And then what we're going to do is we're going to continue finding roots that are found by adding on multiples of 360 degrees over n, okay, or all coterminal things. So the definition, or the theorem for the root of any number, so long as it's written in trig form, is this. We say z is some RCIS theta. And what we're saying is we want to take, if I had some RCIS theta, if I wanted to take, and I would write this down, I'd say the nth root of this, the first thing we do is we say that this is the same thing as RCIS theta to the 1 over n. And then all we're really doing is we're using DeMoivre's theorem here and saying that this would be r to the 1 over n, or the nth root of r, and then we get CIS, and we'd say, well, theta times 1 over n is going to be theta over n. It's just that we have to say plus 360 degrees k over n as well. Okay, so that's the only difference, and I could even rewrite this again. We could say it's the nth root of r. Just take the nth root of the modulus, and then take the angle and split it by n. and add on any number of coterminal things that you need. Okay, so we're going to practice doing this here. And what I say is this: I want to use this theorem for finding roots of complex numbers in trig form to find all the fourth roots of this number here. So first thing I notice is this number is already in trig form. We have 16 cosine I sine 60 degrees. So one thing I want to do is I want to visualize this. My original number is going in a 60-degree direction, and it's, we say 16 units out from the origin here. So we say 16 is our R value here, and we say our argument is 60 degrees. If you can believe me, that's a theta right there. That's better. Okay, so this is our number. What we want to do is we want to find the fourth root of z. So I'm going to show you, if I take the fourth root of z, then what I'm really doing is I'm taking the fourth root of 16 CIS 60 degrees. Now this is kind of hard to interpret. Actually, we can't interpret it this way, but what we can do is we can say that, I know this from algebra, we say that this is the same thing as this number all to the 1 over 4 power. Where now what I want to point out is this: our n is equal to 4, our theta on the original number is equal to 60 degrees, and our r on the original number is equal to 16. So according to what I've got written right here, then my answer is going to be this right here. So I get r to the 1 over n, which in this case is I get 16 to the 1/4, and then I get CIS, and we get the original angle, which we wrote down was 60 degrees. 60 degrees over n, which in this case n is 4. We say plus any number of coterminals. You notice I'm going to put the k off on the side, but also over n, which is 4. So when we simplify this, we have to ask this question. We say, well, first of all, what is the fourth root of 16? What can I take times itself 4 times to get 16? And we get 2. And then inside here we get this. CIS, 60 degrees divided by 4 is 15 degrees. And then we get plus now. 360 divided by 4 is 90 degrees, and this is times some k. So what I want you to do is put this in your back pockets. Congratulations, you just found all possible roots. I'm going to write fourth roots. You should celebrate. You just found all possible. Thing is this: we only want the roots between 0 degrees and 360 degrees. So here's the deal. When we do this, you'll notice that up here on this theorem it says k starts at 0 and goes up to 1, and then to 2, and then up to n minus 1. And the thing I want to point out here is this: if I were to plug in n minus 1 for k, and in this case we have n is, say, 4 in our example down here. If I were to plug in 4 minus 1 for k, then I would say I'd be plugging in a 3 right here, and for this k, which 3 times 90 is 270 degrees, and 270 plus 15, we're going to find out here in a minute, is 285. But the thing is this: what if I plugged in n? What if I counted one more, and I just went up to n, which is the number of the root we're taking? And I plugged in an n down here. In this case, n is 4. Okay, again, n is 4. N times, or which is 4 times 90, which is 360 degrees. 360 degrees plus 15, what I can tell you is 360 degrees would be like an original 15 plus another 360. You'd be here. You get 375. But that would be here, and that'd be the same thing as 15 to begin with. So what we're going to do is this. You are going to systematically, if this is your answer, you have to give me 4 separate answers. And what we're going to do is we're going to list them separately now. But here was the general answer, plus 90 degrees k. What we're going to do is we're going to list this. We say k equals 0, k equals 1, k equals 2, k equals 3. And in each of these cases, we're going to get a new answer. So when we plug in k equals 0, for this k, what we end up with is this: 2 CIS 15 degrees plus 90 times 0, which is 15 degrees. And the next one's going to be 2 CIS. Now check this out. We say 15 degrees plus 90 degrees times, now in this case, 1, which is 90 plus 15, which is 105. Okay? In this one we get 2 CIS. When we plug in a 2 here, 2 times 90 is 180, plus 15 is 195. And then we say down here we get 2 CIS, and in this case we say 3 times 90 is 270, plus another 15 is 285. What I can tell you is these right here, these are all fourth roots of z between 0 degrees and 360 degrees. So a lot of the times what we want are all the fourth roots that exist, or any nth roots that exist between 0 and 360. So in this case, we say that that k value, recall the k value starts at 0 and always goes up to 1 less than the root that you were taking. Since we were taking the fourth root, we went up to 3. And so last thing I want to do is this. I actually wanted to represent all 4 of these in a graph. You'll notice that all 4 of these have the same moduli. Okay, that is, if I were to represent these are all graphed down here, by the way, 15, 105, 195, 285. These are all the vectors right here. And you'll notice that they're all 90 degrees apart from one another, and they all have radii of 2. So they all lay on the circle of radius 2, but they're all evenly spaced. And the funny thing about roots of complex numbers is that they are all always evenly spaced around the outside of, say, some circle here. So that is how you find the nth root of a complex number in trig form. Cheers.